Hello, everyone, and welcome to the chapter talk through for From Social Science to Data Science. This is Chapter 5, Merging and Grouping Data. In this chapter, we're going to look at how to add data to data frames. Now, there's a number of different ways to add data to data frames, and the first one is you might think of as a one-to-one merge, that we're going to add data from one place and just literally add another version of it to the same data frame or to an additional data frame. Then we're going to look at one-to-many merges. That's going to be instances where we have two different data frames again, but one of them is going to have multiple versions of something that the other one's going to want. And so we're going to want to see how we can map the values from one table into another table. Now, kind of the opposite of that is grouping data. That's when you have data in a table and you have multiple instances that all say qualify or group for the same thing. So you might have a series of movies, and you might want to group their rating by genre or by rating. Now, we're going to apply those using an approach called group mean centering and grand mean centering a variable. And we'll see a little more about the details for how to do that later, but it's a form of normalization, and it can really pull upon a lot of the different approaches that we're looking at for merging here, all in one fell swoop. Now, finally, we're going to want to have a look at these operations in SQL as well as in Python, because a lot of stuff actually happens in SQL, and it's instructive to see how you can do that from data on a database, rather than pull down all of the data from SQL and then filter it or group it once you get there. So now to review, when we combine data across tables, we have tables. They have a shape. They have an index and they have columns, so they can only be so big. And we can use that shape to align data. So we can align data by index or by position. Now, if we align by position, as what we see down here, we have a table with 4 users, and they have 4 choices, and then there's 4 flavors. And so if we just, say, stick the flavors right to the end of the data frame right there, then we get something like this. So they've been aligned by position. Now, imagine that instead we know which user wanted which flavor, and it turns out because they were asked at different times or for whatever reason, they're not aligned. So user number 1, they shouldn't get strawberry. They should get whatever's in 0, which is chocolate. And user number 0, user number 2, should get banana. It's in luck there. User number 3, they shouldn't get chocolate. They should get strawberry. So that should be all mapped by index rather than by position, and we can see that happen right there. Now, when we concatenate tables and the tables have an index, it is pandas is going to handle that for you automatically. So we can go over to Jupyter Lab here and have a look at that. Okay, so to remind, when we first start off this, while the data that comes down, or the notebook that comes down from the web would have output in there, I do recommend making a copy and then, of course, clearing all output. Now, for this one as well, you'll notice I'm also going to be using render side by side, which is a feature of Jupyter. And finally, this one is being done with Pandas 2. Now, if you're not sure which version of Pandas you have, you should be able to see it later on, or you can type pandas.version. So just watch once I import this here. Well, actually, we could have just gone pd._version, and it'll print that over there, and it's rendering side by side, so it's printing on the sides 2.03. It's up to 2.1 now, but I'm on 2.03 here, and this is important because pandas, when we merge or when we aggregate, as you'll see later, it has new expectations. And if you don't abide by those expectations, you might get an error. So there'll be a little bit of additional code here relative to the book and relative to earlier versions of the code. So now we can see what we just did there before. We have some lists and some data frames. We're going to make a list, turn it into a data frame. Pretty simple, straightforward stuff there. And now we can add them together. Now, to remind, if you do strings, you can concatenate, and it just adds them together. Now, what happens when we do it with 2 lists? Now we can see there the list just it becomes now a new list of, or rather just adding these 2 together. So A, B, C, D, G, F, K, and you can see it goes through all of them down like so forth. So what happens when you add data frames like that? Does it add one right onto the other data frame? No, that's not what happens. Instead, it actually kind of superimposes them one on top of the other. So we can see here when we added A, B, C, D, and M, N, O, P, they didn't end up in different rows. They just got added together. Now, test frame 3 here had a different dimension. It was wider. It had 2 rows and 6 columns. And so when we see down here when it did that, these extra columns right here, they no longer have any data in them. They used to have the data BB, CC, and these Ws. But because they were added to nothing on a cell-by-cell operation, it ended up being empty. So now we can concatenate those frames instead. So the real way to do that right here is just to use pd.concat, and you'll watch now it adds one, then attaches the next data frame down below that, and finally the third data frame. So now we still have some missing data, but that's because they never had anything for columns 4 and 5 to begin with. But the one that did have something for columns 4 and 5, right here, that is still preserved. So we can show some important things about how to concatenate data and why it's better to concatenate data rather than to append data in pandas. So you can see here, down below, one strategy might be to say, well, if we have a list of choices, zeros yes, ones maybe, no, and so forth and so forth, we could create an empty data frame, and then for each one of them, I can append right here. And so this is pretty sloppy in some ways, but not the least of which is the fact that what happens is it's going to create a new data frame every time you append, and so then we're going to have an increasingly large set of data frames that's going to overwhelm the memory in our computer. So now you don't really see df append anymore. In fact, it might not even be available pretty soon. What we do instead is concatenate them. And so each one of these entries becomes its own version first, and then all of them get concatenated at once. And so then there's not even really much else to see here. It just turns out being just the one data frame, and that's much more efficient with a much better memory footprint. And so returning here, you can see how we've concatenated the data like so. Now, there's some extra details here in the code about how to manage with multiple columns and different kinds of ways of adding things into a data frame. Now, I'm not going to review those too much here, except to just show them as we're going through, and to highlight right here that we can concatenate on a different axes. So you see what I've done here with axis equals 1, we've now concatenated by adding new columns rather than concatenate by adding new rows. So if you see, I can delete that there. And then actually it's probably going to give me, you can see it's going to give an error there because it has a length mismatch, so it won't understand that. So let's just look at what happens there. Now I'm going to remove that back again and say, just to see what happens when we add the index and add it that way. And the problem, of course, once we have this done, is we now have 2 columns with 0, 2 columns with 1, 2 columns with 2, and so forth. So now imagine I want to edit this cell right here, top row A. I don't really have a way indexing the columns to do that without also affecting this one over here. So just watch, I can run that, and now I added or I changed the value for the first row, first column, and then this one happened as well. So the way that we resolve that is to use multi-index data. So you can see here we do summarize some issues with that, with indexing and being able to multi-index your data. And we can see how we do that here in Python. So we use the keys parameter right here, and I gave it the argument of left side vars and right side vars. So what's going to happen now, still is all the same as what we had before, test frame 1 and 2 and axis 1. See up there. But now, we're going to have the keys left side vars, right side vars, and the other index. So now we have multiple indices right here. This will be relevant later because at one point, Pandas is going to introduce a new index, and actually we're going to want to get rid of that index when we're doing some merging. So it's important to be useful, or it's useful to be pretty good at these and identifying the different indices, as well as like their names and how to access the indices themselves. So now if you'll notice, if we wanted to query the left side variables or the right side variables, we can do that a little more directly. So you see here, query a single item from multi-index data. It's C right there, left side vars2 top, left side vars2 top. So you can imagine now, if we wanted to just edit this variable right here, we have a way of doing that as left side variables 0 and top, and set that to be something new compared to what we had before. Sometimes when you have a variable or a data frame, it comes in. It might come in with the columns actually as each of the cases, and the rows end up being variables for whatever reason. In cases like that, you want to flip your data, so that's what we call transposing. It's really simple in Python. You just use df.t, and it will return a transpose of whatever df is. But it's worth remembering that a transpose is not the same thing as like a rotation. So if we were to take these this frame right here and rotate it 90 degrees, what would happen is that row 3 would end up in the first position, then row 2, then 1. It would be kind of reversed order. Column 1 and 2 would be fine if we rotated it that way. But we want to make sure that when we change this, we still have them in the same order, so that column 1 ends up being here, column 2. So instead of a rotation like that, it's more of like a flip. Like it does a 90 degrees and a flip. So just watch what it looks like when we transpose it. And so then we see row 1, 2, and 3, and columns 1 and 2 when we reorganize it that way. And it's pretty simple to see in Jupyter. We're just going to skip right by it there. So now I noticed before what we did when we concatenated, we're taking data, and that's called like a one-to-one merge, because we have one version of the data in one table, and we want to add it to, and it just becomes one version in another table. We're almost like shuffling these things around. But sometimes we want to have things on different scales. So here we have one scale, which we might call the user scale, and in this case, the scale might refer to what we would consider in the rows. And down here, we would have a flavor scale. So imagine these are ice cream flavors, and for whatever reason, each one of them would have really different amounts of calories. I didn't look this up, it's somewhat arbitrary. But nevertheless, what we want over here is not this in row 0, this in row 1, and this in row 2. I mean, coincidentally, we get that over there. But what would happen if we just stick that in right here? Well, would there be a value for chocolate, and would there be a value for banana down here? What we want is for each of these columns here to kind of map on the calorie value for strawberry there, and for chocolate there and there, and for banana there and there. So that's a one-to-many merge. We're taking one version from one table and mapping it onto many versions in another table. Now, how does it know where to map onto? In this case, the flavor becomes the key. So it's going to expect flavor in both tables right there. Now, managing keys can be a bit tricky, and managing when data is available or not in the two different tables can be a bit tricky. So let's walk through the simplest part of the merge statement here. Here's how we would do this, and then we'll look at some important details. So when merging, we have a concept of a left table and a right table. So when we're reading the code left to right, we would say that purple table, equals blue table merge red table. Well, in this case, the blue table is the left table, and the red table is the right table. So when we want to merge, we want to find out what is the key going to be for the left table and for the right table. In our previous example right here, maybe this would be the left table, and the key would be flavor, and in the right table, the key would be flavor. So the key can be the same in both tables, or it can be different in both tables. So in this one, we could call it flavor, and this one, it could be flavor with an uppercase, or maybe flavor with American spelling without the U in there, and all sorts of things. But we know it's referring to the same thing. So we would either want to stipulate it's the same index, or we would want to stipulate what is the left index and what is the right index. So imagine this isn't just a column in your data, but this is the index of your data. So you can merge on that, or you can merge on a specific column, and you can do that for either table or for both of them. So we can see here left index equals true is one argument, or you can have left on column name. You can't have both of them because it's either going to be you're going to be merging looking for the key in a column or a key in the index. Now, in addition to what we merge on, we want to think about how we merge. Imagine over in our table right here we had another flavor, salted caramel, and nobody ordered that flavor. So what's going to happen during the merge? Or what if we have another user and they entered something and for whatever reason they didn't add a flavor? What are they going to get for the calorie score? Basic ice cream, perhaps. Maybe this is a topping, and so there might be, in theory, something missing right here. So that suggests different ways in which we think about merging. And I always had a bit of trouble kind of wrapping my head around this part of it until I figured out that keys, in this case, are pretty similar to or represent the same thing as sets. So let's take a little diversion into set logic, and then we'll go back and we'll have a look at the rest of that. Now, before we do that, let's see that merge really simply in Python. So in this case, I'm using countries and territories of the United Kingdom, and here we have the 4 countries there, but we also I've included Jersey. Now, that's going to be relevant below because I have another table here. This right here is going to be the country df table, and this one right here is people, and it's going to be a people df table. And there's nobody here from Jersey. But also, we have Idris here, who's from the Isle of Man. And now look, we don't have a score for the Isle of Man up here. So what's gonna happen then? First, let's run that, so we can see here's our table right there. Now I'm going to do that merge. So country df left on country right index equals true. Okay, so let's see what happens when we follow through on that. What's the left on country? Left is people. So in this one, we're going to merge on the people. Now in the country df, it says right index equals true. So in this, yes, look at that. The country names are the indices. So we'll want to map them onto the values in the country column. So watch this. And there we go. And so now the populations have been imported. So Northern Ireland, 2 million people. And we have a column with 2 for, or representing 2 million roughly, for each of these 2 right here, 3 for England. These values might be a little bit out of date, but it's here to show the concept and not to do specific demographics. But if you were to do those demographics, you'd want to get this merging right first. Okay, so now before we go down to this little bit here, let's go back and look at it in the PowerPoint. So sets define inclusion and exclusion. So they don't have an order, and there's no duplicate items. So that's just a refresh. So imagine we have a list here, 1, 1, 1, 2, 2, 3, 6, 9. So there should, if we have it as a set, you'll only have 1, 1, only have 1, 2, and 3, 6, 9. So that's what it'll look like if you do that there. You can ask for inclusion. Is 1 in this set? And it would be yes. Is 4 in the set? Well, it's not in the list. It's not in the set, so it will be false. So you can use this for true and false. Now they have these curly braces just like dictionaries, because dictionary keys operate like sets. You can only have one key in a dictionary that's the same thing. So you can't have 2 number 1s as keys in dictionary, or 2 word apples as keys. So now we have set operations. Now that we have these, it's worth thinking about set operations. And let's start with some sets here. I'm going to say one is a set of the first 5 odd numbers. So we'll say set 1 is odd. And we'll have set 2 is sequential. Now this is the first 5 numbers, 1, 2, 3, 4, 5. So you can already see that there's going to be some shared between these 2 different sets, but not entirely. So the union of them is if we combine all of them together. And so we can see here, if a number is included in either of these, it'll be in the union of them. The intersection of them is the things in common. So let's have a look up here. What ones are in common? I think the number 3 is in common, the number 1, and the number 5. So yes, the intersection here is just the numbers in common rather than all of the numbers that are shared by either of them. And we can also do something like subtraction, so we can take the first set and just exclude the second one. Now you'll notice the second one has more numbers in it than that weren't even in here to begin with. So it doesn't throw an error. It just takes away of those in here which are in here, and vice versa. Okay, so now let's have a look at how sets work again really briefly in JupyterLab, and then we'll go and see them as a sort of join. So first, here's our sets. We can see what we've done here. I've got some duplicates as a set, and then we can turn that, I guess, into a series. Now, down below here, we can see, and I'm going to just move this back a bit. You can see the union from both, the intersection, and that's for our sets, pretty similar to the ones that were shown in the slides. Now that we have these sort of sets done, now let's go back and think about how they relate to joins. Well, if we have joins, we have keys, and those keys, just like dictionary keys, they can be considered as sets. We don't have to think of a column like it could be a set. Columns can have multiple things in them. The time that we do that is when we want to think about a one-to-many merge. Because in a one-to-many merge, we have to have one of the columns has to have just one version of each of the entries. And it can go to the other one. That's many. Okay, so now let's have a look here. We have a merge, and the default kind of merge is called an inner join. So let's have a look at that. So an inner join here, we have Alice, Bob, Cam, and Dot, and from England and Scotland. And then we have these countries over here, Wales and Northern Ireland, and they're not mentioned in this country. So when we join the data in, they're not kept. So that is like the intersection. The intersection is only the things in common. Now, a merge, an outer join, is like a union. It's all of the things in common. So just watch our keys here. We have Wales and Northern Ireland. They're going to show up if we do an outer join. But now, what will happen with an outer join is that we might get some missing values because these weren't in this original table, and in order to absorb all of the data from both, it's going to just say, well, I don't have something for name, or in this one right here, for country. So let's go back and have a look at how we might think about these different joins here. An inner join is the default one right there, and we've lost Jersey, but we've also lost Idris over here. Idris, where we probably shouldn't have lost Idris. Now, if we do an outer join, we keep both of them. Now, interestingly, Jersey right here, because we did merge on an index, and it came, now its index is missing. And so this could lead to all kinds of trouble. Now, if you can uncomment this right here and see, replace index equals true, and then now that gives us a nice tidier index. You really only want to do that if the index doesn't matter, of course. Now, a left join right here might be what we want to do in order to preserve Idris, even though there's a not missing value. See right here, the inner join said if someone isn't in the second table, then they're gone. And if there's a value in the second table of country, we don't want it. But perhaps we do want the ones in our people table, and if there's a missing data, then it doesn't matter. So that's our left on country, right index equals true, right here. And you could do a right join, but normally you want to structure your data, and you can see you get this problem right here. Normally you want to structure your data so that you have a sense either of it being an inner join or a left join, and you want to keep that. It's like your table of interest is on the left, and then the things that you add to it are the table on the right. Now, merging data is a way of taking, one of these things and mapping it onto many of the rows. So we're kind of adding new data that way. But what if we want to do it the other way around? So all those people who had the strawberry ice cream, imagine we have some feature for them, like times they've been to the store. And so now we can see, well, what's the average number of times that they've been to the store? Do the people who have strawberry, do they come more frequently than the ones who, have chocolate? For a lot of transactional data, we would want counts. Things like average number of friends, how much activity is happening. Are they say tweeting a lot? how many tweets, and things per categories. So when we summarize data in groups, we use what's called an aggregation. So we want to group our data, and then we want to apply the same measure to each one of the columns that's been grouped. So we can think of this as the split, apply, combine method. And we've already seen that method implicitly with the value counts. So, a value count splits the data into subgroups. So that's the split part. Each subgroup has the same value. Maybe it's all the strawberry values. Back to the ice cream. And then it counts how many elements are in and applies, and then combines these results. So the count is what is being applied to each group. So we can see that right here. We have a distribution. Some numbers right here. They're not in any real order. It seems like there's a lot of ones. So when we make a series from this list, we can do this thing called value counts. You may have seen already, we can also just do that in a list with the collections package in Python, but I like showing it here as a value counts. So what we have, this is our index, which turns out to be these numbers to begin with. And then we have the value of them. Now, how is that split, apply, combine? Well, first we split into groups. The groups of the 1s, the 2s, the 3s, the 4s. We apply count, which gives us this value. And now we combine them right here. And in this case, it made the original ones the index and the counted values the result. Now, when we aggregate our data, sometimes we want to just look at that aggregation. You might want to say, how many people per county or city. But sometimes we want to do those aggregations in a way that we can make use of them back with our original data. So first, let's have a look at how we might see that in Python. First, let's group some data right here. So here's our data frame. It's going to be called peopledf. I didn't display it on the side there. Perhaps we could, just to confirm what we have. And there we go. And we have an age value and a tweets value right here. So if we want to group by tweets, or if we want to group by country, then we can use this sort of code down here. Now you will see this code earlier on, group by country.mean, and it's not going to work with the new versions of Python. And so let me show you what sort of error you're going to get if you try to do that. So I'll just run that right here. And it's going to say not implemented error. It's like, oh my goodness. And if you keep going, this one is a really, this is a doozy of an error. And when you get to the bottom, cannot convert Cam, Farah, Hannah to numeric. It's like, oh goodness, what is going on with that? What happened is that this peopledf, it cannot group by and take an average of the name, this name column. And for whatever reason, the name column was stored in there as in some different order than it has here. So Cam, Farah, and Hannah showed up first. But now then, how would we manage that? In the old one, what it used to do is say, if you're not a number column, I'm not going to aggregate you, I'll just ignore you. Now, the new one, it's a bit more tricky, as it happens, or at least as I've surmised with the new Panda code. And you can see that right here. What we have to do first is we have to explicitly just exclude the variables or the values that are not numeric. So down right here, instead of group df, peopledf, first we should just select down to country, age, and tweets. We know that those are the numeric columns. And then group by country, and then it'll work. We can see that here. Like so. Now there are ways that we can do that a little more automated as well. So we can do this select types include number statement here, and that would give us age and it would give us tweets in our original approach. It wouldn't give us country though, so we'll have to see what happens then later because country is not numeric. Country is going to be the grouping variable. So let's watch this right here. Well, first we say group df. This is going to be some interstitial group df. It's going to be people df, like this, select types number. So it's just going to be those number columns. And then we're going to add a new column for country. Say group df equals people. Now this is a bit lazy this way, but it does work pretty fast. And it's useful for this sort of exercise right here. Now, in a generic sense, you might, depending on how you merge, you might want to make that a little more automated. So here's one way in which we can make that a little more automated. Right here, I say select from the original peopledf these columns, where the columns are the union of the columns from this and this column right here. So that's how we might do it in one line. Now, I kind of alternate between the two right now, especially because sometimes I will want this country value in the index. But both of these are ways in which you can then just select down to some numbers and a key. Okay, so now we can see that we have it grouped. So we don't get an error anymore, nothing terrifying. And you'll also notice what we have done here is we've grouped by each of these, and we have now values for age and tweets for each of the countries. Now I want to go and back up and show that right up here. If you'll notice what we did up here, group df, people df, group by dot mean, and then it showed up like so. Now, when we go down here to this one, you'll see we have age, sum, and mean. Age, tweets, sum, and mean. And that's because we actually aggregated by multiple different measurements. So now let's go back up and have a look at that again. I just said group by country dot mean. So that was one form of aggregation. So we can put lots of different aggregations in here and do something to help summarize our data. So for example, max will get us that there. Now if we wanted to do just mean in such a way that it was similar to what we had above, we can do mean right here in this. But now if you'll watch that, we have to make sure that our parentheses are all right. Because remember, we're displaying the formatted table altogether. So just watch this. And there we go. That we don't have mean and sum up here. We have only just those in the column. So this is a single index. But when we did it the other way around, what we had was a multi-index. And that's going to be relevant because later on we're going to want to manage that multi-index to get at this data a little more cleanly for our centering. So to mean center a variable would be to take its value and then subtract the mean from it. So if it's above the mean, then it's going to be above the mean by that much, or going to be above 0 by the amount that it used to be above the mean. Whereas if it's below the mean, then it'll be negative. It'll be that distance from the mean is now going to be that distance from 0. So it's pretty simple then. You just take the mean of any value. So we would calculate the average age value, and then we say, age minus the average age value. And that can be a new column. That's now mean centered. Now let's go have a look at that over here. And so for grand mean centering, again, this gets a bit tricky in Python. We're going to use some mean values here. Just look at this. Our age value, the average was 32, and our tweets is 1639. That's the average number of tweets of all these people right here. Of course, it's clearly that there's some outlier, but this tends to be what you see with data like activity data on a platform where you have really skewed data. So maybe mean centering is not the right value depending on your model, but to show the exercise, it's still pretty relevant here. So we have age this, tweets that. Now, what you see right here is a series. Now this series is because I did 2 different values. Now how are we going to mean center 2 different values? Well, I'm going to use a for loop right here because it's really we only count 0, 1, or n. So even though it's 2, I'm still going to use a for loop. And I'm going to say for each of the indices right here, one is age and the other is tweets. Now go back and make a grand mean value. I'm going to display that value, but actually then I'm going to get rid of it because I don't want it. I just want to show it for the display. And the thing is that in building a real data set, I may want to keep that in. It's almost certainly that I would keep it in. But as we go on later on, screen real estate gets a bit tight for the demos, so that's why we're going to delete it afterwards once we've shown it. Okay, so let's see here. We have the name, the country, the tweets, age grand, and tweet grand. So the age grand here is minus 2.2. Why is that for Allie? Well, you see the average age is 34.2, so now their new value is 2.2 or minus 2.2 rather than 32. And the same for the so that's grand centering of a variable. But what if we want to group mean center a variable? Now, group mean centering means that we would take the say the average per group and see how does one's value compare relative to the group specific rather than the global specific for a value. Okay, so the first thing we got to do to remind, and this is in Python or pandas too, we want to isolate the numeric columns. So what I have done here is we're going to group it by country. So I first select the numeric types, and then I add by country. Now we're not grouping, we're not changing the dimension, so that way I can just add in the country value like this. Okay, and so then we group that one and create a new interstitial data set right here. This interstitial data set is going to have the things that we're going to use for the mean centering. So everyone in England, we're going to want to subtract 35.7 from in their age value. For Isle of Man, it's going to be 40. And for the tweets, here's how many we're going to subtract from anyone in England, their tweet value. Now you will notice, and I'm just going to sort of scan back then, this says age, tweets, mean, and mean. And this is like what we had over in Python. You can see here we have like these sum and these means. And you'll see that down again in the exercise right here. So the third step then is to clean up that multi-index. We're going to drop that level right there. And that's how we would do that. Now, if you weren't sure which level to drop, just to check to see that level 1 is the one at the bottom, 0 is at the top, and they always keep going, increasing in value as they go down through the columns. Okay, so with this interstitial data set, now we're going to merge it back into the data frame. And so here's a command for that. And you'll also notice we now have this new suffixes parameter right here when I've given this argument. So this is what the suffix is going to be for the left-hand side and for the right-hand side. So if we have any variables that we merge in, such as age or tweets, the original one, or the left-hand side one, peopledf, is not going to have a suffix, whereas the right-hand side one, groupdf, is going to have this suffix right here, _gmean. So it's going to look something like that. So we've merged our group means back into the data. And now that we've merged our group means in, the second step is pretty straightforward. We just subtract the group means. But now you'll notice what I've done here with the group means is that because we had multiples of them, I did this thing here, filling in and just adding new variable names so that we have age mean, and now we have this GC right here. And you can also style it. This has been styled from the output in JupyterLab. So we see we have those right here. They're grouped and they have this extra level. Now when I get rid of it, there's no level. Now you notice this time I didn't style it, whereas up here I did style it. And so that's what accounts for the differences in the number of zeros. Now down here we can see I'm going to add it, and we've added our mean values, but we haven't centered our variables yet. That means we're going to have to subtract this value from the person's value. So now that we have the new data frame right here with the level dropped, you can see we've dropped the level of the column right there. Then we can take that and we can now use this in order to mean center our variables. Well, the first thing we're going to want to do, of course, is merge them in. And you can see I've merged them in, and I have some suffixes here. We're going to have no suffix for the left-hand side, and then this _gmean suffix for the right-hand side. So when we look at the variables later, we're going to see that group mean variable. So now we're almost ready. We're almost done. We have the mean values per group, but we haven't subtracted the original values from them. So we can see here, for example, Ali is from Wales, and the average was 3,200, but that's because Ali was the only one from Wales. Whereas for Northern Ireland, we have these different groups right here. We have these two people, so adding them is 226. The average is 113. And so now to get the group mean centering, we're going to want to go through each one of these and subtract. Now, I've made it a little bit complicated for myself by doing two variables at once, but that allows us to see how we can do that in an iterative fashion. So down here, as you can see, for each of the columns, I'm going to give it this name right here. grand-centered or group-centered for each of the ones that are group meaned. Now you'll notice that down here, what I've got done is put a little format dictionary in there. What that means is that only those columns which will be keys in the format dictionary are going to be formatted according to the values that we specify over here. So on the right-hand side, we can see 0.1f, and I've given both of the group mean and the mean centered variable the same values. We can actually give them a different value if you wanted to see the output of that, but all the other values are not going to be changed. Now we do that rather than just saying style all of them to be 0.1f, because some of these here are strings and they can't be formatted in that way, and so the program will give an error. So we iterate through and add that into our formatting, and this is what comes out. Now we can see it's a bit off on the page there. We can move that over. And yeah, we see all of our group mean centered. Ali, remember, was the only one there, so their value is exactly 0 right at the group mean centered variables, whereas the others, it varies a little bit depending on how many are in their country and what their specific value was. Now, before we get to SQL, one last topic that I wanted to speak about in terms of merging and grouping is one way of reshaping data. And this is a way that can be pretty common in data frames, and it's where you have one column, and inside that column is a collection. So it might be something like a number of tags for a particular row or post, or it could be a number of friend nominations for a particular person, which is what we're going to see right here. So you can imagine you have a data frame where you have the name of someone and the number of other people that they nominate. So Ali here nominated Dot and Ellen, Barb nominated Cam, Cam nominated Ali and Barb, and so forth. And so this here is the basis of a network file. We can consider this a kind of wide edge list. But in many cases, we want to have a row per relationship right here, not a row per person and their nominations. It might be Ali nominated Dot and their friends, Ali nominated Ellen and their workmates, or something. Also, this will allow us then to have a single row just for that relationship in case if there's other features we want to add to it. So in order to do that, we'd want to make this a long table rather than a wide one. So we can use explode in Python for this. And we can see that Dot has 4 nominations. So why don't we just say 4 over the maximum, we'll make 4 new columns, and then we'll have 1 column for each of them. Well, the problem with that situation is that you don't really know how wide those columns are going to be, and if you add someone else with 5 nominations, do you now have to rewrite all of your variables? And being able to do this in a long format rather than a wide format is much more robust for that reason. Now let's have a look at it. We can see here, once we've exploded, we now have 1 row per Ali and Dot, and then 1 for Ali and Ellen, and so forth down the line. Now imagine that instead of this, you do happen to have them in their own column. So you have nomination 1 is Dot, and nomination 2 is Ellen, and nomination 3 is Cam, and so forth. Then you can use a different command. You can use melt for that as well. Now going from long to wide is a slightly different situation. Right here, this is not necessarily the sort of thing where you can aggregate as easily as you could by grouping these variables, but you can aggregate if you do first group and then some sort of iterations over it, but it can be a bit tricky. Fortunately, most of the time we're not doing that. We're doing it the other way. Before rounding off the chapter, I wanted to introduce SQL. So many but not all databases are some variation of tables. Now databases can be data stores in some way that are not premised on tables. As you know, we have data we can store in a tabular sort of row and column format, but we can also store it in a nested format. So some databases like MongoDB will store things in a nested format. And there's other novel databases like graph-based databases, which will store things in a network or graph-like object. But the vast majority of databases will be in some sort of tabular format. They'll also be stored in some way where you would access them through SQL, or structured query language, which really is quite amenable to the tabular format for databases. So you can access multiple tables from the same database and combine them. If you create a database, it can have multiple tables, much in the same way, I guess, like a Microsoft Excel document or spreadsheet program can have multiple worksheets, where each one would have a little tab on the bottom. And you can reference them between each other and combine them. You can apply grouping operations on the data, just like we saw there, and you can ask for specific columns. So within SQL, there's some different flavors depending on the database type, whether it's like MySQL, Oracle, or SQLite. Now in Python, you can access those in a number of different ways, but I guess the two most common paradigms for this are the object relational mapper paradigm, or the I guess I'm not really sure what they call it, but just the simple get the data from SQL paradigm. Now, the object relational one is one where you work with the tables on the server, much like you would databases or data frames in pandas. You can say, dot something for the column name, and a program like SQL Alchemy is really nice for that. So if you have a really clean sense of what data is in your database and how you might want to interact with it, SQL Alchemy can be quite useful. On the other hand, sometimes it's a lot simpler to just write the query in SQL directly rather than in some sort of quasi-Python, and then send that query to the database, get the data back, and then from that data, then start working in Python. And that's like SQLite or the SQLite 3 package. In both cases, you're going to want a connection to the database, and you're also going to want a cursor. And the cursor object is going to help you fetch the data. The connection is going to get the data from the server. So SQLite is a means of storing data in a database, which is written as a file on your computer. You probably have lots of little SQLite databases in different parts of the computer. And so it's different than a database which normally was run on the server. For those, that connection is a connection that can be often authenticated, come through an internet address. SQLite can exist on your computer, so you don't need to worry about the internet. You can just access it as if it was a file without running a database server. So in order to set it up, it's pretty easy. Once you've imported SQLite, you can just create a connection to a database. If there is no database where you create that connection, it'll create it for you. So in the current version here, I've created one called example.db. And the first time you start that, if there's no example.db in your directory, then one will be created. And then you get a cursor, which allows you to interact with it. And so the first thing we would do with a cursor, if we have an empty database, is perhaps create a table in that database. And we use a table schema in order to delineate what's going on in that table. So in this case, our schema has things like an ID, which is an integer, and a primary key. Then we have name, which is going to be a text, and it's going to be unique. Age is an integer, country's text, and tweets are integer. So it's pretty similar to the sort of data structure that we saw in Python. But there are some detail differences. You'll notice that some of these are in uppercase. That's more by convention. SQL generally is not case sensitive, but we often put these commands in uppercase. Now you'll see here that we also have integer primary key. Primary key means that each of these integers is going to be used for indexing. It also tends to be a unique key within there. Now, even though the integer is a unique key, we also have decided to say that name is going to be a unique key as well. So if you try to add somebody with two separate names in there, even if they're two different people, it's going to be trouble. Now, age, we didn't say anything like unique or primary, so people can have the same name, they can have the same country, and they can have the same value for tweets. And once we create that database, it's just going to be a shell. There's not going to be any information in there. And if we say cursor.execute, that means the cursor is going to do that statement, but it doesn't mean that the database is going to receive that statement. That's what we do using the commit command. Now, the reason we use commit, as we can see in some of the Jupyter Lab data, is because we could have a database that is being written to by multiple people for multiple reasons, and what we would want to do is send a bunch of queries off at once so that the database makes sure that everything is aligned across the different users reading and writing. So let's have a look at that over here in Python. Well, we could skip over from the long versus wide data, but it's pretty straightforward and easy to see how that could happen. And now in the database here, once again, we're going to specify our data directory. So to remind whatever directory that we're in, so if I show, and this is from GitHub right here, so I have this in chapters, the data directory is going to be the parent directory, up one, and then goes down into data. Now you'll see I've already created an example database, but I'm going to delete that right now just to show you what happens when we create this. All right, so it's not going to throw an error. We're going to connect to this database example.db, and then it should create it. So run that commit statement, and then we look over here, refresh, and we see example.db just got created. Then it said create table integer, with all the structure right there. It's a bit clumsy, but now if I drag this out, we can see the order that I've put in there. Now down here, we can see for I in range, len people df, blah, blah, blah. What it means is that for each of the ranges of people, I am going to, by position, get their index and then insert them into this database. So that's going to be a lot of insert statements. And again, it's another reason why we would want to queue them up in our cursor and then commit them all at once, especially if that's over the internet. These sorts of things could be very slow if not all done en masse. Now I run that and we don't have any feedback from that right there, but it is in our example database. You can view an SQLite database without using loading it into a server, but you would need another program for that. There are examples I give in the book of the SQLite browser or the DB browser for SQLite, which is freely available and you can explore it. But the other way that we would explore it is just within Python itself. And so in this case, we can do that using pandas. We don't even need to use SQLite 3, not directly at least, by running some queries. We can do it in pandas here with this read SQL. First we read star from the users, and then we pass it the connection. And so the database should have those users in there, and we run that connection, and it'll be fine. Now just to confirm, say imagine that I did this. Delete that database. We run this database up here, and once again, it'll create the example database. It's right there. And I haven't added any data, so now let's see what happens when I run this. We get nothing back. We get just a shell of data, but we get the variables. It didn't give us an error. It's just that the data wasn't there to be returned. Okay, so you can actually see in Python how, or in SQL, how we would do a lot of the same operations that we did in terms of grouping and filtering data, or even merging that data, much like we had done in Python. So the first here, as you can see, is that we can filter, to select name, tweets, age from users where country equals Scotland. Now, never mind these quotes in PowerPoint, as sometimes they auto-correct them. It's always meant to be these double ticks or 3 ticks for literals right here. Actually, before we go on to the more complicated one, let's just show that. So down here, we can select count from users, an example of that, and that will aggregate these. We could select count name, country from users, group by country. Now just watch that, how that grouping was. In this case, the aggregation was count, and we didn't attach it to some object or anything. We just said select a count of that name and country from users group by country. Now, why didn't we say count for country there? Are we going to? The thing is that because it's the key, so it's only going to show up once. So just watch this. We had 3 users from England, 2 from Northern Ireland, and so forth and so forth. That might be similar to a value count statement as well in Python, just by counting by group. Now they get a bit more tricky here. Now look how I've created average of tweets in this case. selecting in through there. And so now we have the average come out. If we wanted to do some group mean centering, it could be a bit more tricky. But here's a way that we can, I just want to show using multiple different forms of aggregation at the same time. Also, see up here, we've got the index. Right there, I've hidden the index. Down here, we have an order by average tweets descending, which says so we can even do the filtering. Right there was just all over the place, and now we can see the average tweets. On average, we would say those in England tweet the most according to this fictitious data. And now, finally, we can have a look at if we have a second table here. You'll notice what I've done is I inserted the country values. Up here were the people values. So of course we grouped by country, but it was the people DF, as we can see right here. Maybe moving that back a little bit. Now if we create another table, as I've done here, called country, then we can do something really neat, like merge the two of them together. So if we see here in this statement, users.name, age, country, country.population. So we had a users table which had name, age, and country. And then we had a country table which included a name and a population. So what you'll see here, the age was only in one of the tables, so it was pretty unambiguous, although we could have said users.age. Country was in both of the tables, and so we don't have to stipulate because it's just going to be the same value, because as you see, we have inner join country on country name equals user. So that's how SQL would do that same sort of key linking, and here how they would set the inner join as compared to how you would see it in pandas. But the logic is pretty much the same. That's also it for the Python code for that chapter. As you can see here, I'm giving another example of how you might combine a bunch of those things there. So now to summarize, we could think data comes in different shapes and different scales. Last week, or in the last chapter, we would have looked at data in hierarchical shapes versus tabular. But not only within tabular do we have data at the same scale. We can have things representing a row for a person and then a row for the country that the person lives in. We can link data across these scales when the data is aligned, and that's where we use keys. The first way, the simplest way we show was position, and that was the most fragile. Indexes work, but that allow us to only map one with one index to one with the other index, and key allows us to do one to many merging. Now the way we join tables makes a difference, as I noted. An inner join keeps where there's a key in both tables, whereas things like a left will keep all from one of the tables, even if there's missing data. Now we can reshape tables too. We saw how to transpose them. We saw how to aggregate and combine these tables. And that's in addition to the skills from earlier chapters where you look at things like using a mask to filter down the table itself. We saw these operations in SQL as well as in Python. And it's often preferable to do things in SQL or to think about how you might do them in SQL if you are querying data from a database server or elsewhere. You can be tempted to download all of the data and process it locally, when in fact there might be very significant differences in how much data you have to download and how much processing you have to do if you can use SQL in order to limit the data on the server and then bring it down and work with it. So if you want to apply these skills, there's some ways we can think about this. The first are some, thought experiment questions. So here we have, imagine table of posts and a table of comments on those posts. So you have some YouTube videos called YouTube DF, and each video has a comment. So now we can have a second data frame with comments per video. Now, why do we need two data frames? First off, think about that. Well, of course, we need one data frame because the unit of analysis is in the row, and the first one is videos. So it would have like the video, its name, its URL, maybe the person who uploaded it, whatever. And you can have a second data frame with the comments. So you may have comments that are across multiple videos, but each comment is going to have its own features. Things like who made the comment, how many upvotes, is it a banned comment, is it blocked? And you don't need to have one data frame for all the comments for one video and another data frame for all the comments from another video. You can have one data frame of videos, another data frame of comments, and then only merge them when they're appropriate. But now think about it. What sort of measures will we include in the YouTube vids data frame from just the video? What can we add from those videos? Likes, views? Now, what's the most reasonable key to link these? Have a think about that. Think about, is display name the most reasonable? Is display name consistent on YouTube? What if people change their display names? Is there an extra ID that you can use? What measures could we get to aggregate from the comments into YT videos? So we have a video and we have comments. Maybe things like the average upvote score or how fast it was between comments. You can explore these different issues, but think of them as part of the conversation dynamics that's happening on the website. What objects do each of the comments have, or features do the comments have, that in aggregate could be of relevance to your research question? Now imagine we have a users table as well. So we're getting a lot of tables in here, but this is getting close to what we really see in the real world. Users can have comments across videos. Users could post videos or post comments. Maybe users have like a date that they joined or a detail about where they're from. And now when we combine the data from the users, as well as the comments and the videos, what questions can we ask of that? And how can we aggregate or merge them all in such a way that we ask our questions most appropriately? We'll be considering a little bit more of that in the upcoming chapters, where we look at Reddit, Twitter, as well as research questions and how to compare and explain things in data. But that's it for now. Thank you for watching, and have a great day.